Hi everyone, myself Harshita S. I'm currently pursuing my 6th SEM in Sri Venkateshwara College of Engineering. So today we are talking about the system software and compiler. So in that the very important topic that we are talking about is the SIC architecture. So first, before going to the topic, we'll see what is the system software. So system software consists of a variety of programs that support the operation of a computer. So the SIC architecture. So we have to see what is SIC basically. So the simplified instructional computer is an hypothetical computer that includes the hardware features that is most often found on real machines. SIC consists of two types of format. So they are nothing but the standard model, that is nothing but the SIC, and next is the SIC that is the extended version of SIC. So now we'll see what are the instruction formats, data formats, memory registers that include in the SIC architecture. So first is the memory. So in memory, the maximum memory available on SIC system is 1 megabyte, that is equal to 2 to the power of 20 bytes. And registers. So registers are nothing but in SIC, there are 5 registers. So including that, we have additional 4 registers. Those registers are D, S, T, and F registers, and they're provided by the SIC. And there is a 48-bit floating point data type, and the B stands for the base register, S stands for the general working register, and T stands for general working register, and F stands for the floating point accumulator. Now we'll see what is the instruction formats. So basically there are 4 instruction formats. So these instruction formats are very important in order to decide the location of the particular instruction. So we'll see what is the instruction formats tell us. So in that we have the format 1. The format 1 consists of 1 byte and it contains only one operation code. Format 2 consists of 2 bytes. So the first 8 bytes are for the operation code and next 4 are for register 1 and the following 4 are for register 2. So the numbers for the registers go according to the numbers indicated at the register section. So format 3 will consist of 3 bytes. So the first 6 bytes contain operation code, next 6 bits contain flags, and last 12 bits contain the displacement for the address of the operand. Now the operation code uses only 6 bits. Thus the second hexadecimal digit will be affected by the values of the first 2 flags, that is N and I. Next, the format 4. So format 4 consists of 4 bytes. So that is same as format 3 with an extra 2 hexadecimal digits for addresses that will require more than 12 bits to be represented. Next is our instruction set. So what is this instruction set? We'll see. So the SIC provides all of the instructions that are available on the standard versions. In addition, we have the instruction that has to be that will load and store the new registers that are nothing but the LDB, the STP, etc. So these floating point arithmetic operations that are the addf, the subf, the multiplyf, the divf registers, they'll perform the move instructions. And then the move instructions are RMO, that is the register to register, and the arithmetic operations ADDR and SUBR and MULR and DIVR, and the super call instructions that are the SVC. Next, we'll go to the input and output. So we all know that there are input and output channels that are used to perform the input and output. And here the CPU is also executing other instructions while these input and output format will be continuing, and allows overlap of computing and IO that will result in more efficient system operation. So the instructions SIO, TIO, and HIO are used to start, test, and hold the operation of this input and output channels. So we'll see the very important topic, that is the addressing modes. These addressing modes and flag bits are very, very important. So we'll see what this flag bits and addressing mode stands for. So the first one is nothing but the direct. So the direct register. So in direct, we have the direct consists of X, B, and P all set to 0, and relative either P or B equal to 1 and the other one will be equal to 0. So immediate is nothing but the hash value. In hash, I will be 1 and the remaining will be 0. In indirect, the I will be 0 and N will be 1 because N stands for indirect, and indexed is X is equals to 1, the rest will be 0. And you can see the types of addressing modes here. that is the base relative and the program counter relatives. So these are the two addressing modes that are in SIC XC architecture. So the mode is nothing but the base relative, and indication is nothing but here B will be 1 because it's base relative, and the program counter will be 0. So the address calculation will be as follows. That is target address is equals to B plus displacement. So this value should be within 0 till 4095, and the program counter relative. So in this, the base relative will be 0 and the program counter will be equal to 1, and the target address will be in the format till -2048 till 2047. Now the format 1. So we can see how the formats will be written. So for format 1, as indicated, it's of 1 byte, and the opcode consists of 8 bytes, and the register consists of 4 bytes each. And then the format 3. The format 3 consists of 3 bytes. That is opcode is consisting of 6 bytes, and N, I, X, B, P, E, these all will consist of 6 bits, and then the displacement is of 12 bits. Next, here the format 4. So opcode will be 6 and the rest will be till 6, and only the address will be of 20. Moving to the program format. So the program format consists of three formats. That is nothing but the header record, the text record, and then the end record. So header record. So the header record consists of, first column will be the header. The second column consists of 2 to 7. Within that, you have to write the program name, and next column consists of 8 to 13, within which we are writing the starting address of the object program, and next column will be writing 14 to 19. That will be the length of the object program in bytes. That is the hexadecimal values. So the next one will be the text record. The text record is consisting of, first column will be of text, and second column will consist of the starting address. The third column is about the length of the object code, and the fourth column is about the object code that is represented hex. Next, the end record. The end record just consists of the starting address of the executable instruction. All these should be written in the hexadecimal values, which is a very important. Next, we'll solve the particular problem to understand better how the instruction formats work. So this is nothing but the SIC XC problem. So here, the main things that we need to keep in mind is nothing but we have to found out the location. We have to find the object code. So these are the two things that we need to do, and then we will have to write the program format. So first, the particular this particular column, we will have to find this particular column. This is nothing but the location column. So this particular column will be the location problem, and this second column is nothing but your label column, which will be provided, and next will be the opcode column, and next will be the operand column, and this is the object code column. So first we'll find out the location column. So how to find out the locations? So to find out the location, so as you can see in the operand column, that is you will have to find from the operand column. So the location of the first instruction will be the same thing. That will be 105D. And for the location, that will be 105D. And the location for the next instruction will be based on the instruction formats. So as I already told you that X is a instruction format 2. To decide which instruction format that each operand will stand, first we will have to check what are the contents that are present in the particular operand. So here we can see X. So X is a register. So already discussed in instruction format 2, we have one opcode and 2 registers. So this is the instruction format 2. So we have one opcode and we have 2 registers. So the X will stand for instruction format 2. So when it is instruction format 2, you will have to add for particular 105D the 2 bytes. So if you add 2 bytes in hexadecimal values, it will come to 105F. So that will be the location for the next that will be the location for the instruction X. Next, length. Length is nothing but the instruction format 3. So instruction format 3, we have to add 3 bytes. So when you are adding 3 bytes, it will be 1062, and output also is instruction format 3. So when you are adding again 3 bytes, it will be 1065. And W loop is also again we have to add the 3 bytes, which is again an instruction format 3. So it will be 1068. Now buffer comma X. So buffer comma X is also an instruction format 3. So no, here we can see the LDCH. So LDCH, in before LDCH, we have plus, which indicates it's an instruction format 4. So the difference between the instruction format and instruction format 3 and instruction format 4 is nothing but if we get any opcode, that is beside the opcode, if we get a plus symbol, that indicates it is an instruction format 4. So when it is plus, we are telling it is an instruction format 4. So we'll have 4 bytes. So that comes to the value of 106C. So next output is again the instruction format 3. So we are adding the 3 bytes. That is nothing but 106F. And next is T. So T again, as I told you, it is an instruction format 2 because it's consisting of a register. So when it is of register, we will add again 2 bytes. That is nothing but 2 bytes. That is nothing but 1072. Next, W loop. W loop is again instruction format 3. So we are adding 3 registers. That is 107F, 75. And for R sub, it is also an instruction format 3. So we are adding again 3 bytes. That is 1078. Now here you can see the byte. So byte always stores one value. So 1 byte will be equal to 8 bits. So we'll have to add 1 byte, means 1 value to the particular location. So again, you can see the register is X. So we may get in confusion that X is an instruction format 2, but here X is storing some particular values. So we can see that it's storing 0 and 5. So 0 consists of 4 bits and 5 consists of 4 bits. So 4 plus 4 is 8. That is 1 byte. So this particular 1 byte will be added to the next location, that is 1079. Next we are getting the RESB. So in RESB, we are getting 400. So 400 is nothing but you will have to in this, we have little difference when we compare to the previous locations that we have written. So what happens here is 400. So 400, we will have to convert it to hexadecimal values. So when you convert it to the hexadecimal values, you'll get one particular value. That particular value should be added with the previous location. That is 1079. When you add this 1079 with the hexadecimal value of 400, you'll get 1209. So this is the instruction format for RESB. Next is 2. So here also we are storing 2 bytes. So we are adding the 2 bytes, that is 120B. So this is with the location. So next we are coming to the very important part in this particular problem, that is to find the object code. So how do we find the object code? So object code is again very simple, but for this we will have to check with the instruction formats again. So now to find the first particular object code, so first we will have to check with the operand. So here the operand is nothing but X, and since it is instruction format 2, the particular instruction format we have only 844. So we just have 16 bytes to store. So first is for opcode and next is for the register and next is also for the register. So when we see here, it consists of only one register, that is X, and the mnemonic value of X is nothing but 1. So what you have to write is for clear X, for clear, they have already given the value, that is the B4. Since they have already given the opcode, that is B4, so B4 will be written in the hexadecimal values. So the hexadecimal value for B is 1011 and 4 is 0100. This is written in the form of 8 bytes. So when you write this for 8 bytes, next is nothing but the register, that is X1 and then X2. So here X is only 1. So we'll write the hexadecimal value for 1, that is 001, and we don't have another register, so we are writing 4 zeros. So this will complete the object code for the first operand, that is X. So we will have to underline this particular thing for 4 bytes. When you underline it for 4 bytes, you will get the object code for the particular X instruction. So it is nothing but 1011 stands for B, and 0100 stands for 4, and next stands for 1 and 0. So B410 will be the instruction object code for X. Next we'll come to the length. we'll come to the length. Length is again instruction format 3. So instruction format 3, as discussed, the format will be in this form. That is, the opcode will be 6 bytes and NIXBPE will be again other 6 bytes, and next 12 will be the displacement. So should represent the length in the form of format 3 instruction. When we come here, so the length value will the LDT value should be represented in opcode. That is, here is nothing but 7 4. So when you represent 7 and 4, you will have to represent it in the form of only 6 bytes. So when you represent it, so for the value for 7 will be 0 1 1 1, and next will be 4. So 4, you know, the value will be nothing but 0 1 0 0. So we will, since it is should be represented in the form of 6 bytes, we'll write the first 2 digits, that is nothing but 0 1. So this completes the opcode portion. Next is nothing but the NIXBPE. So N, and now we can see there is no indirect value, there is no immediate value, there is no indexed value. So what we'll have to write is, when nothing is there, so there is no indirect value, so N will be 1, and there is no immediate value, so N will be also 1, but and there is no X value, that is index value, so it will be 0. So to decide the base and program counter, we will have to perform the object code first, and here E, the value of E always will be 0 in the format 3, and in format 4 the value of E will be 1, and this is another major difference between format 3 and format 4. So to decide whether B and P will be 0 or 1, what we'll have to do is, so you have to first find the length, the opcode for the length. So the opcode for the length is, the location for the length is 1209. So it will be 1209, and the length of, and you have to find the location of the next instructions of LDT, that is 1062. So you will have to minus 1209 minus 1062. So to repeat it again, so the length opcode or location of length is given here, that is 1209, and the instruction of the location of next instruction is nothing but 1062. That will come to an answer of 1A7. So this will have to be written in the 12 bytes. So you can write, you can see here 0001 will be 1, and A will be 1010, and 7 will be 0111. So here, when this is in the, this particular 1A7 will be within the values of the program counter as indicated here, that is minus 2048 till 2047. So hence program counter, in that case the program counter will be 1 and the base counter will be 0. So here program counter will be 1 and the base counter will be 0. The base relative will be 0. And next we'll have to find the object code. So 0111 will be 7 and 0111 again is 7. And next 4 bytes are nothing but 2. And next it is 1A7. So this is the object code for length. Next, to find out the object code, we will have to see with output. So we have to, for output, it is TD. The opcode is TD, and TD consists of values E0. So we are, since this is also an object format 3, so we will represent again it in the form of E, and E is, the value is 1110 and 0. So the first 2 digits, that is 00. Next, to decide the values of Ni, we do not have any indirect value, we do not have any immediate value, we do not have indexed value, so it is 0. And we decide the values of the program and the base relative. So E will be 0 because it is in format 3. So to decide this value, so first it is given as W loop. The label will be given as W loop. So the location for the W loop we'll find out. So the location for the W loop is 1078 and 1078, and then the instruction of next format is 106. The location is 1065. So when you subtract it, you will get to the value of 10013. So this is within the values of minus 2048 till 2047. So again, program counter will be 1 and base relative will be 0. So when it is, when this comes to an format of E32013, next we'll come to the W loop. That is nothing but the JEQ. So JEQ is again the same thing. So we have the opcode, that is 30. sorry, 30. So this 30 has to be represented in the 6 bytes. So it is 0, it is 0011 and 00, and this will be based on, there is no index value, there is no immediate value, there is no index value, and the program and base counter will be decided later, and E is 0. And we can see that here we have W loop again. So W loop value will be 10778, and it is next is nothing but 1062 minus 1068, and it will come to the form of FFA. So this FFA should be written in hexadecimal values, and then you will have to write the bytes in the form, you have to divide 4 blocks, and then you will have to write the object code. So it will come to the format of 332 FFA. Next is nothing but LDCH. So LDCH is nothing but instruction format 4. So this instruction format 4, you will have to just do one thing, that is you have to write the address in the form of 20 bytes. So here we can see the LDCH value is nothing but 50. So the 50 is 5 and 0 is written here. And since there is an index value, you can see here, that is X. So we are writing X as 1 and N and I as 1. And the base and the relative counter we are not taking into consideration, because it will be 0, 0 in this case, because it is instruction format 4, and E will be equal to 1. Next, so the LDCH, the buffer X, so buffer is nothing but 1079. So this 1079 will be the format of this 1079, and the location of the next instruction, that is nothing but 106C. So when you will do this, you will get to a format of 1079. So 107, no, we'll have to just see the location of the instruction format buffer, that is nothing but 1079. So we'll directly write this 1079 in the form of hexadecimal values. So this will come to an object code of this particular value. Next is nothing but output. Output is again an instruction format 3. So for output, the WD, the value is DC. So we have written in the form of opcode. Next, there is no indirect, indexed, and immediate. So we are giving it as the particular those values. And to decide the program counter and base relative counter, you will have to find the output location. So the location for output is 1078, and the next instruction location will be 106F, which is nothing but the 009. So you'll have to represent it in the form of the hexadecimal values. So when you write this, you will get to the format of DF2009. Next is T. So we all know the instruction format for T is nothing but 2. So since it is having a register, so I'll represent it in the form of the 844 opcode values. So this T value consists of T is nothing but its value is nothing but your 5. So mnemonic value is nothing but 5. So we'll represent it in the form of 5. And since only one register, the next register will be 0. And opcode is nothing but we have to see the TIXR, and it is B8. So we are representing it in the form of 8 bytes. So it will come to a format of B850. And next is W loop. W loop is also in format 3. So for W loop, the value is 1062, and the instruction location of the next instruction is nothing but 1075. So it comes to a format of minus 013. So when it comes to the format of minus 013, you will have to find the 2's complement. After finding the 2's complement, you will have to write that particular value in the form of hexadecimal values. So repeating it once again. So whenever you get a minus value, you will have to find the 2's complement, and whatever you get in the 2's complement, that has to be written in the hexadecimal values, and that particular value should be written here. So when you represent it in the 2's value, you will get it as FED. So this FED should be written in hexadecimal values. So the object code will be 3B2FED. Next is the R sub, and as we all know that R sub, there will be no particular instruction format, it will be common. So it is nothing but R sub is nothing but opcode is 4C. Just we'll have to write the opcode in the form of the 6 bytes. And next is there is no index, indirect, base counter, base relative, there is no program counter, and so we'll have to write everything as 0, and the particular address will also be represented in 0 bytes. So this is how we write the object code. So the main things that we'll have to remember in this particular problem of SIC is nothing but we will have to first see which instruction format each one will stand. So based on that, we'll decide what are the locations for that. If it is instruction format 2, we'll add 2 bytes. If it is instruction format 3, we'll add 3 bytes. If it is instruction format 4, we'll add 4 bytes. And to differentiate between instruction format 3 and 4, it is nothing but the plus symbol before the opcode. Next is when we the one more major difference is nothing but E will be equal to 0 in instruction format 3 and E will be equal to 4 in instruction format 4. So this will be the way we will write the object code, and object code should always be written in the form of hexadecimal values. Next is nothing but the program format. So which is a very important thing. So program format consists of, as discussed earlier, I have already said that it consists of 3 parts. That is the header record, the text record, and the end record. So first we'll see what is the header record consists of 1 byte. So here it is starting with the header part. Next is nothing but the starting address of the particular instruction. So starting address is nothing but the WRREC. So that has been written here. Next is nothing but the location of the first instruction format. So that should be written in the form within the addresses of 8 to 13. So within this particular bytes, we have to write the instruction. So that is nothing but 8 to 13. It consists of 6 bytes. So it will consist of 6 bytes. So 105D. And before we are adding 2 zeros because we have to represent it in the format of 8 to 13. Next is nothing but the length of the this particular instruction. So the length, to find out the length, we will have to minus the first instruction with the last instruction. So when we minus the first instruction with the last instruction, we will get it as 1AE. Since we have to represent it in again within the 6 bytes, that is nothing but within 14 to 19, which consists of 6 bytes, we'll add 3 zeros before it. Next is nothing but the text record. So text record also consists of first T and next the address of the first location, that is nothing but the 105D. Next is 1B. We'll discuss this later. Next is the length of the instruction format. So the length is nothing but you will have to write starting from all the object code, that is starting from B410 till 05. So when we have to write it till the 05. And now to find out 1B, what we will have to do is we will have to count the each variable and each number, that is starting from B410, that is 1, 2, 3, 4 till this particular 05. So when we add all these numbers, we come to a number of 54. So 54's hexadecimal, we have to convert this particular 54 to hexadecimal value. That is nothing but 27. So the 27 will be the decimal value and the hexadecimal value of 27 will be 1B. So this particular 1B is written here. Repeating it again. So B410 till 05 should be counted and the number will come to a format of B4 and B4's hexadecimal, B4's half will be 27 and 27's hexadecimal value will be 1B. So this 1B is written here. And next, the third column is nothing but the end. So it is nothing but it will have E and then the location of the address of the first instruction, that is 105D. So it is written in the form of 6 bytes. So I hope you understood the problem. Thank you.